In this lecture, we are dealing with bending moment. But what is bending moment? We go for that. Before that, we start with what is moment. Force into perpendicular distance we call as moment. Then what is bending moment? That is the algebraic sum of all the moments taken at any section is known as the bending moment. As an example, this is the reaction Ra, and if I want to take the moment at this point, Ra into x, that is the clockwise moment, and at section 1 we call it the bending moment. If I want to take the moment at this section, suppose over here, then Ra into this, that is a plus b, clockwise, you can see it's going clockwise like this, and w into this distance, which is taking an anti-clockwise moment like this. So the net moment at B will be Ra into a plus b clockwise minus w into b anti-clockwise. This is called the bending moment. Means nothing but bending moment is nothing but the taking the moment at any section. As x increases, bending moment increases. X decreases, bending moment decreases. This is all about the point loads. Similarly, if we want to see the bending moment pattern for a uniformly distributed load, then suppose this is uniformly distributed load at a distance of A, right from A, with a small w as kilonewton per meter, but the total distance is A plus B. Now, if I want to take the moment at x section from A, then let us see how much will be the total load. It is W into X, and which is acting at a distance of x by 2 from this end and as well as from this end. So the moment at xx will be W into x is the total moment load multiplied by the Cj of the load from here, x by 2. Now it comes out to be W into x by 2. Which is clockwise or anti-clockwise? Yes, we find that it is anti-clockwise. So we can say if they take the moment at xx, it is anti-clockwise. If we solve this bending moment at any xx, it will be w x square by 2. Now here, x square terms come to the picture. That is the indication that the bending moment varies not as a straight line, but it takes a curve like that, a parabolic shape. So wherever there is a uniformly distributed load, it will behave like a parabolic shape, curved shape, and where there is a point load, it will behave like a straight line. Similarly, if we want to find out the bending moment at B, it will be the total load is W into A acting at A by 2, and distance from here to here is A by 2 plus B. Now you can see bending moment as B, so W into A is the total load acting at A by 2 plus B, again anti-clockwise, and we'll find that will be a curve right from here to here, it is a parabolic curve, and right from here to here there is no UDL, it will act as a straight line. Now we'll try to solve few problems. Over the bending moment for a simply supported beam with a point load acting at one point. Suppose this is the problem. AB is the span of 6 meter length. At 2 meter from a 50 kilonewton load is applied, and reaction is 33.33 and 16.6, and that we have already calculated on previous examples. Now you start from here. The bending moment at A is nothing but Ra into 0. You see, bending moment at A is equal to Ra into 0, it is 0. Bending moment at C. means nothing but only we are considering the left portion. So RA into this distance AC, that is 33.33 into 2. Again it is a clockwise. You see 33.33 into 2. It is the bending moment at C. If I take the bending moment at B, take the moments of all the forces about B. That is RA into this distance clockwise minus 50 into this distance anti-clockwise. That is 33.33 into 6. This is with a plus sign, and 50 into 4 with a minus sign. That will give the bending moment at B. That 33.33 into 6 minus 50 into 4, it turns out to be 0. So one thing that we find so far, where there is a simply supported at the ends, bending moment at supports must be 0. Bending moment at the supports must be 0. Now we'll go for the next type of problem, which is with a 2-point loads. We have already solved all these problems in the beginning for finding out the reaction as well as for the shear force also. Now, here again the span is that of 8 meter, and at 2 meter and 5 meter from A, there are two loads of 40 and 60 kilonewtons. Now the reactions are 52.5 and 47.5. Starting from A, RA into 0. Bending moment at A is equal to nothing but RA into 0. If I take the moment at C, how many forces are there just to the left of C? Only one. Because it is nothing but 52.5 into 2 and 40 into 0. You can see it will be only 42.5 into 2 clockwise moment, and clockwise moment is always taken as positive. So it is to be drawn only above the reference lines. If I take the moment at D, bending moment at D starts again from A. That is RA into this distance clockwise and 40 into this distance, because taking the moment at this point it is anti-clockwise. It is anti-clockwise, and 60 into 0. So we can find the bending moment at D is equal to 52 into 5, that is 2 plus 3 clockwise, minus 40 into 3, 60 into 0, and you will find the bending moment at D will be equal to 142.5 kilo Newton meter. Similarly, when we take the bending moment at B, RA into this distance clockwise, 40 into this distance anti-clockwise, 60 into this distance again anti-clockwise, and the total summation must comes out to be 0 whether we take the moment at A or at B, because when it is simply supported, the final bending moment turns out to be 0. Yes, it comes out to be 0. There is again a systematic calculation is to be done while going from left to right. Always consider the clockwise moment as positive and anti-clockwise moment as negative. Now we'll take example for an overhang. We can very easily calculate the reaction as well as we can draw the shear force diagram. Now, again start from left end and reach to the last end of E. So we are starting from A. The bending moment at A will be nothing but 28.75 into 0, because there is no perpendicular distance. If we come across this 20 now, so bending moment at C will be, how many forces are there just to the left of C? Only one force. So take the moment of all the forces which is just to the left of the particular section at that point, that is RA into 2, again it will act as a clockwise moment. So it is only to be taken as RA into 2, that is 57.5 clockwise, so it is plus. If the moment at D, then RA into 5 minus 20 into 3, because this is anti-clockwise, this is clockwise. Just see. RA into 5 minus 20 into 3, that comes out to be this one. And if we take the moment at B again, it should not be 0. because it is not there at end. End is somewhere over here. And here you will find it must be 0. Let us see. RA into this distance, that is 8. RA into 8 minus 20 into 6 minus 40 into 3, and it must be equal to how much? That you can see, that is B RA into 8 minus 20 into 6 minus 40 into 3, it comes out to be minus 10.0 kilonewton meter. Up till now it was giving plus sign, now it is giving a minus sign. So now the curve will be, the bending moment diagram will be shifting from positive to negative between D and B. Finally, if you take the moment at E, start from A, reach up to this. RA into AE clockwise, 20 into CE anti-clockwise, 40 into DE again anti-clockwise, and RB into BE clockwise, it turns out to be 0. And the diagram can be these all positive, this comes out to be nil, it comes out to be 0. Being a point load only, we are finding that it is a straight line only. We'll go for the overhang on both sides now. We are taking all different cases for the point load first. As usual now, again you will find various 2 point loads at the 2 overhangs just to the left of A and just to the right of B. As usual, find out the reaction, draw the shear force diagram, and start taking the moment from E itself. 5 into 0, it must 0. Just see, I am starting from C. 5 into 0. Now I will take the moment at A, just to see to the left of A, how many forces are there? Only one force. That is acting anti-clockwise. Minus 5 into 2. Minus 5 into 2, it must come as minus n. If I take the moment at this point, see how many forces are there just to the left of this. 2 forces. One anti-clockwise, otherwise is clockwise. That is 5 into 3, it is negative, and RA into 1, it is positive. So if we go for D, minus 5 into 3 plus RA into 1, again it is positive. Now from negative it has shifted to the positive one. Take the moment at E, take the moment at B, and finally when we take the moment at E, you will find it must be 0. For that, take the moment of first force, that is 5 into this distance anti-clockwise, RA into this distance clockwise, 80 into this distance anti-clockwise, then 20 into this distance again anti-clockwise, RB into this distance clockwise, and 10 into 0. And when we find that this is minus 5 into 10 first, then RA into 8, then next will be 80 minus 80 into 7, then next will be the 21, that is 20 into 3 plus RB into this distance of 2 meters. And if we make the algebraic sum of that, it turns out to be 0. At the end, if it doesn't come out to be 0, means there is something wrong in making the calculations of calculating the reactions. Recheck your calculation and correct value of the reactions is to be calculated. Otherwise, if these ends are coming to be 0, means we can say our all reaction calculations are correct. Up till now, we are just talking something about the point loads. Now we start with UDL. We have already seen in the first 2 pages, just to calculate the moment at any distance, because the reactions has already calculated. The 20 kg per meter for 4 meter and 2 meter is without any load. Suppose taking the moment at any distance x from here, it is RA into x minus W into x acting at x by 2. So if we take the moment at A, it will be 53.33 into 0. If I take the moment at 1 meter from him, A, RA into 1 meter, just see, RA into 1 meter minus 20 into 1 meter acting at 1 by 2. Because this is 1 meter, this much load right from here to either 20 kilonewton and which will be acting at the half of that much. So it is 1 by 2. Similarly, 2 meter, 3 meter up to 4 meter. When we go up to 4 meter over here, it is RA into 4 minus 20 into 4 acting at 4 by 2. Anti-clockwise. This is anti-clockwise and this must be clockwise. This must be clockwise. This must be clockwise and this must be anti-clockwise. This must be anti-clockwise like this. And finally, when we reach up to B, that is the 6 meter from here, we can find that it must come out to be 0. And we find yes, it is coming out to be 0. Now we have to find out that point where the value of the bending moment is maximum. First of all, we have to find that point where the shear force changes the sign from positive to negative. And we have found that the shear force changes from negative to positive will be at a distance of 2.66 something. Yes, it is 2.66 meter from the left hand support. If I take the moment at a distance of 2.66 meter, that will give the maximum bending moment anywhere in between the diagram. Yes, now just see, we have already calculated the value and it comes for 53.33 into 2.66 minus 20 into 2.66 acting at 2.66 by 2, it is 71. Amongst all the values we have seen, this will be the maximum. This is most important thing to know, that how to calculate that value where the shear force changes the sign, that will be the value of maximum bending moment. This was just talking something about the single UDL acting at a distance of some 4 meter from one support RA. Now there are two UDL acting at different distances with different magnitude and the different length. As usual, calculate the rate. As usual, calculate the reactions RA and RB. Start taking the moment from here. First of all, this point, then this point. When you are coming across this, then it will be RA into this minus 10 into 2 acting at 2 by 2. Just see. 32 into 10 is C up to C. We will come across the D now. 32 into 3 minus, because it is anti-clockwise. It is anti-clockwise like this. So it is minus 10 into 2 acting at 2 by 2. Similarly, when we come across E now, again RA into this distance, that is 6 meter. RA into 6 minus 10 into 2 acting at 2 by 2 plus 3, that is 4. Just see now. If I take the bending moment at A, RA into 6 minus 10 into 2 acting at 2 by 2 plus 3, that is 4. And finally, when we reach up to 0, it must come out to be 0. Similarly, in the shear force diagram, we have seen at a distance of 6.6 meter from here, the shear force changes the sign. Taking the moment at this point, take this into 6.6 minus this into 5.6, this into 2, this and this like this. And you can find out the maximum bending moment at a distance of 6.6 meter from A is 122.8 kilonewton meter. You can see amongst all the bending moments we have calculated, you are getting the maximum bending moment at a distance of 6.6 meter. If it is less than 6.6 meter or more than 6.6 meter, the value will be always less than 122.8 kilonewton meter. So it is important to find out that point where the shear force changes the sign, and from positive to negative, and there you will find the maximum bending moment. Previously we were just talking something about the overhang for a point load. Now I am talking the combination of the loading. Combination of the loading with a uniformly distributed load along with the point load also. Because systematically we started with a point load, then we have marched up to the UDL. Now in this example, we are coming across for UDL plus point load. Similarly, calculate the reactions and take the moment, and finally you can get the result like this. You can find the result like this. You can solve yourself and you will get the result. The same type of problem, again I am just expressing over here, is like this. Now here, I have solved this problem by not only solving only the bending moment. Now it is a combination of the two diagrams, that is the shear force diagram and the bending moment diagram. And here you will find that the shear force changes the sign from here to here, which is a distance of 0.5 meter from here, that is 4.5 meter, and then we can find out the maximum bending moment at a distance of 4.5 meter. So find out the reaction, draw the shear force diagram and draw the bending moment diagram, and after drawing the bending moment diagram, pick up this point and take the maximum bending moment either from this end or from this end. You will get the same result as you are calculating from this side or you are calculating from this side. Another example like this. 2 point loads, 1 UDL, again reactions, shear force diagram, change the sign from here, we can say plus to minus, find out this point, it comes out to 1.86 from here, plus this much distance of 4 meter, so it is 5.86, and you will find that the maximum bending moment you will be at a distance of 5.86 meter, and it is 54.66. Rest of all other bending moments you will find 54. So it is most important to find out this point first. So first of all, find out the reaction, draw the shear force diagram, draw the bending moment diagram, and pick up this value where the shear force changes the sign, and then finally find out that bending moment where the shear force is 0. It must get the maximum value for the bending moment. It must get the maximum bending moment value. Coming to the last part of this simply supported as well as overhang, the same problem with different loading, with different point loads and different uniformly distributed load for overhang also. Again here you will find there are 2 points where the shear force changes the sign from here to here. So we'll have to find out the shear force over here also. We have to find out, the bending moment at this point also, and the bending moment at this point. This will maybe this is negative, this is positive to negative, again this is negative to positive, like this. And again same thing, just calculate and you will find the bending moment will be, it cannot, my final bending moment at E as well as A must be 0. E and A it must be 0. A it is 0 and at E also it is 0. After this, we will go for cantilever type of beam. It was all simply supported. Now we are talking something about the cantilever type of beam. It is very easy. There is no question of any reaction. Whatever the load, the same load will be resisted by the reaction support itself. If W is this load, reaction is this much. This much is the load, no other load, so shear force will be only W, continues right from here to here. Now whether it is clockwise or anti-clockwise, it is for a cantilever it is always be taken as negative because it has got the convex shape. Convex shape, whether it is this direction or this. So whenever there is a convex shape, the bending moment or the shear force should be treated as negative and will be drawn below the reference lines only. Just like in this case. If I want to find the shear force, it will remain same 10 kilonewton, again here 10 kilonewton, again 10 kilonewton, again 10 kilonewton, throughout it will be 10 kilonewton. But if I want to find the bending moment, 10 into x and 10 into 1 and 10 into 2 or something, go on increasing, and you will find that bending moment will be, this is suppose 10 into 2, so this is already done 10 into 1, this is shear force 10 constantly going on, and 10 into 2, that is 0, starting from 0 reaching to 20, and it is a convex shape, hence always taken as negative. So if instead of a single point load, that would have been a 2-point load. There is no question of plus or minus sign, only all time same sign, and just like this. What is the shear force diagram? 10 downward, 20 downward, add it, that will be the total reaction, that is the total shear force diagram. There is no question of plus or minus like that, as we are talking in terms of simply supported. Similarly, the bending moment. In case of UDL, it will be curvature like this and a straight line like this. W into x acting at x by 2. Finally here, WL square by 2. W into L acting at L by 2. Then such type of combinations are there, permutation combinations are there. You can go through this, solve the problem, work at home, and then we'll find a, and come prepared with all the things, and we'll see how that can be compared. So you are supposed to draw as a homework for this cantilever type of structure with a UDL and a point load combination, and then you have the comparison like this. Some problems are already given over here. You are supposed to solve it and find it the answer. Thank you very much.